Welcome, ladies and gentlemen, to the 2021 Williston Basin Petroleum Conference. This is part 2 of our geology session. My name is R.C. Nessett. I'm a geologist with Ness Consulting Service. I'm co-chair with Ed Murphy, North Dakota State Geologist with the North Dakota Geologic Survey. Our first presenter is Francis Nwachukwu. Francis is a PhD candidate in the Harold Hamm School of Geology and Geologic Engineering at the University of North Dakota. Francis today is presenting on Diagenesis, porosity, and petroleum source beds of the Birdbear Formation within McKenzie County, North Dakota.
Good afternoon, and welcome to my presentation today. Today we'll be talking about Diagenesis, porosity, and petroleum source beds of the Birdbear Formation within McKenzie County. This was my master's thesis that I wrote towards getting my master's degree at the University of North Dakota. Bear in mind that we want to see if we could knock Team Nesheim off his feet a little bit in terms of what the statements he made for the Birdbear. So let's go. Looking at the Williston Basin, we can see it's an intercratonic basin that sits in the heart of North America. It is kind of like over 250,000 square meter in terms of extent and coverage within the heart of North America. It is present across South Dakota, North Dakota, Montana, Saskatchewan, and Manitoba. It has been speculated that sediments here range from Cambrian to Quaternary, but Halabra in '82 gave the peak deposition, kind of like started in Ordovician towards the Devonian time within this illustrious basin. Leroy in '82 gave us that rock units within this basin range from marginal marine carbonate to fluvial sediments. And according to Murphy et al. In 2009, he discovered 20 different formations have commercially produced oil and gas within the North Dakota portion of the Williston Basin. We're looking at the Birdbear, as I said today, and we can see from the North Dakota chart of the stratigraphic column, it is overlain by the tree forks with some regional conformities in certain areas within the basin. And is underlain by the Dupro Formation. The Birdbear is kind of unique in terms of you can easily identify this formation within the logs. You can trace this over a regional scale within the Williston Basin of North America. We know that the Birdbear Formation is a carborite evaporant sequence according to Burke and Sparr in '82. Bearing in mind, from the Schlumberger report of 2020, it's estimated that over 60% of the world hydrocarbon reserve and 40% of gas reserves are stored in carbonate formations globally. The Birdbear, as you can see, it was noted that it has 2 units that are recognized from lithologies, lithofacies descriptions. Based on what we can see the lower carbonate dolomite limestone unit, which have variable fossiliferous limestone and dolomite facies. That is what we are looking at, the lower carbonate dolomite limestone unit. And we also have an upper anhydrite carbonate unit, also what we are looking at up over there. This is kind of like a cyclicity in terms of deposition. You have limestone, dolomite, anhydrite, limestone, dolomite, anhydrite cyclicity as we have reoccurring within the horizons of the Birdbear Formation within the Williston Basin. Shallow marine to Sapka environment has been given as the environment of deposition for the Birdbear within the Williston Basin. Taking a look of the map you're looking here is a cumulative production map of the Birdbear across McKenzie and Williams counties. And it's estimated that the Birdbear contains approximately 2,313 million barrels of oil within the Williston Basin, but recoverable, it's about 644 million barrels that can be technically recovered, according to Lefevre in 2009. And from the map you're looking at to date, we can see that over 25 million barrels of oil equivalent has been produced within the North Dakota portion of this basin. These are from over 180 vertical and horizontal wells as of 2015 from the Oil and Gas Review. But the B zone within this formation is the primary reservoir for vertical wells. The A zone is also kind of like important for secondary wells. But the A zone has been targeted by dozens of horizontal wells towards the south of the basin. Prior to we getting our research done, we had objectives, questions we asked ourselves. What are the reservoir characteristics of the Birdbear in relation to the level of diagenesis, porosity, and permeability? What is the reservoir porosity trend in terms of distribution within the storage area of McKenzie County? And is the Birdbear self-sourcing? Just like Tim pointed out that the Birdbear does not have enough source rock, but we're going to see if the Birdbear has sufficient source rocks that could serve in terms of hydrocarbon production within the Williston Basin. We looked at what is the total organic content of the source beds. Are they mature enough? Are they sufficient for hydrocarbon generation? And lastly, we kind of like asked, are these source beds, are they extensive for us to have them enough for hydrocarbon production within the basin? To further work further to get our results, we looked at McKenzie County, which sits at the middle part of the basin. We looked at data from 1,143 wells. Out of these wells, definitely we had about 13 of these wells that had cores that we're able to look at in terms of getting our findings. And within these wells, 7 of them have distinct sections, which we looked over 110 slides. We looked at core descriptions and lithofaces identification to identify the types of lithofaces that are present within the Birdbear. We correlated these facies to help evaluate the extent and scale of the Birdbear within its units in the basin. And then we looked at those distinct sections to see the level of diagenesis within the rock fabrics and how do they relate in terms of reservoir qualities. We also looked at nuclear magnetic resonance. We used these to correlate the types of porosities and permeabilities that are bound within the basin, or the sediments rather. Lastly, we looked at source rock program paralysis. And we used this to evaluate the source beds, the types of kerogen present, and to see if they are really mature enough for hydrocarbon production within the sediments of the Birdbear formation. Based on our results, we are able to confirm, yes, there were 2 A and B zones. The B zone is with the porous dolomitized facies. And these dolomitized facies, we can see, act as the reservoir rocks. And then we have the bank facies, especially the amphiporas, which kind of like gives us the source rocks or the source beds that were used or that serves as a source bed for oil generation within this formation. This is the physical core representation of the lower dolomite facies of the Birdbear formation. And these are the bank facies, most especially the amphiporas. These are the type of amphiporas we have within the Birdbear. So this is just like the physical representation of how these amphiporas kind of like what they look alike in the core slab, the core repository in Grand Forks. We looked at the upper anhydrite carbonate unit, and we also discovered that, yes, 2 units, 2 or 3 thin bed dolostones kind of like exist within this unit. We also have anhydrite couplets and also dolomitized limestone beds that are also porous within this A horizon. That is the A horizon we have over there. And that is the limestone facie that you're looking at right there, and that is the anhydrite facie that acts as a seal to kind of like locks out whatever hydrocarbon potentials we have within the Birdbear formation. This is a paleogeographic facie map of the Birdbear. This was from Jeffrey Bader in 2020, where he talks extensively on the sequence stratigraphy of the Birdbear and also the structural implications of the Birdbear within the Williston Basin. We can see how neatly the bank facies and the other facies we have within the Birdbear, how they line up. So McKenzie County being our area of study, we can see we have enough bank facies that would serve as source for the Birdbear within the McKenzie County, or within the Williston Basin, rather. We went further for correlation and lithofacies identification. We were able to have the correlation done on our wells, and we can able to see how the stacking pattern is of the formation and its sediments across the Williston Basin. Based on stratigraphy, we are able to kind of like pinpoint to discuss, to see how the B zone or the A zone, in terms of how the abundance of suspects, are they visible enough? Can we correlate them? Are they thick enough for them to serve as suspect within the Williston Basin? So from this map, we can see that the A zone has well appreciable suspects that could be of a foot or inches that you can trace within certain areas within the basin, but they are not extensive within the Williston Basin. But the B horizon, definitely, we have about over 2 feet of source bed, and you can laterally trace this source across the Williston Basin. So giving us that, yes, we have mappable source bed thickness within the Williston Basin. We looked at types of porosities that are bound within the Birdbear formation in terms of diagenesis and their genetic properties. And we're able to discover that we had the VOGI porosities, the solution-enhanced porosities, the intragranular, and the intragranular porosities. In all, the VOGI porosities are the least in terms of percentage, about 17% across the sediments we studied, but they are more prominent in the B zone. And we also have the highest percentage porosities being the intergranular, having 34%, while the intragranular has 28%, and the solution-enhanced porosities here, we are close to 21%. So these are the types of porosities we have within the basin. And in all, we're able to reach that higher diagenesis activities equals to high dolomitization. And if you have high dolomitization, it prepares you, the reservoir, for good quality in terms of storing hydrocarbons within the formation. As I said previously, high diagenic concentrations with various phreatic zone characteristics were prominent, and these gave rise to mineral dissolution, reprecipitation and recrystallization of these minerals, and further dolomitization, which also gives us our intercrystalline and intracrystalline porosities that we were able to find within the sediments of the Birdbear. The VOGI porosities, we also note were kind of like enhanced, solution-enhanced porosities also. But in all, hydrocarbon production was from extensively dolomitized stromatoporoid banks. These were from either stratigraphic, structural, or both combined traps within the Williston Basin. This is a chart based on our nuclear magnetic resonance spectroscopy results. We're able to show that some sediments gave us high porosity. As we can see, sorry, I don't have the pointer. If you look at the graph on the left, you can see about we have 90% porosity in terms of dolomite porosity. While the one on the right, we can see a little appreciable. Oh, okay. This was the dolomite facies. We can see about over 19%. But in all, we have about 4.3% in terms of overall average porosity. While on some limestone, we have kind of like intermediate, about 6.5%. But in all, we have an appreciable value for limestone to be 4.5%, while we have the intermediate giving us something in between. But in all, the average permeability values were about 4.8 to 20 millidarcies, and hydrocarbon presence are in the dolomite facies, and they are about between 7 to 92%. For the NMR results, we're able to use to check out the cutoff of the limestone and dolomite facies, and we were able to see the clay-bound water, the capillary-bound water, and the free fluid. And we were able to discover that the free fluids dominate the dolomite lithology, as more clay-bound water and capillary-bound water kind of like more within the limestone lithology. In all, we can see the free fluid. Sorry, put this back. How can I take this back? Sorry, I jumped a slide. Okay, figure that out. So as we can see, the free fluids we have about 7 to 92%, while the clay brown water we have about 2 to 68%, and the capillary brown waters were for about 6 to 65%. The dolomite ecology here, as we noted, are the reservoir, which holds more of the producible fluids, which are the hydrocarbons within the bed bed. So we can see free fluids to be about 7 to 92%, which we can see here within the dolomite facies. So that indicates that the dolomite facies definitely holds much of the hydrocarbons within the Birdbear formation in the Williston Basin. For that correlation, we were able to see how porosity is kind of like trend across the basin. So we looked at some of our wells to see how the porosities are bound. We can see well 2967 has kind of like a poor porosity, while we have intermediate porosity with our well 2602 and 1962 wells. Then, as you can see, the highest porosity was from 12249 well, which we have high porosity within that area. So that's the highest porosity we have, and then both intermediate porosities and a low porosity. So we kind of like try to see, okay, how does sedimentation go with porosity? So we made the sedimentation map, which is the isopath map of the Birdbear formation, and also a total porosity map of the Birdbear formation. As we can see that we have low porosities within the middle part of the McKenzie County, which is our study area. We have mixed porosities at the northeastern portion of the basin, which you can see was 2967 and 3080. And we also have a high porosity at the southwest portion of our study area. If you look at the isopath map, you can see that 12249 well has the highest porosity based on our previous slide. And definitely we can see it falls within the high porosity zone area. So taking a look at this map, we can see that our porosity decreases as we move from the north towards the southwestern part of the study area. So that tells you the more sediment area you have towards the north, you kind of like lose your porosity. But I believe while we have a mixed porosity within the northeastern portion would be as a result of the anticline, the Nesheim anticline, will be probably kind of like helping organizing or kind of like re-enhancing the type of porosities that we have within this area. But all in all, the lower you move towards the study area, you have higher porosity, while towards the middle part, you have kind of like a low porosities within this sediments. We also looked at other results from other research to see how they come up with in terms of total organic carbon constitution for the Birdbear formation. As we can see, Sigler in 2015 was able to find total organic carbon content of about 11.5%. Engelmann also had about 6.87, while we had about 2% on kind of like most of our sediments. So this is just trying to show us that the Birdbear formation within the Williston Basin has the appreciable amount of total organic carbon to serve as a source in terms of hydrocarbon generation. So taking a look at our Van Crevelen diagram, which is the plot of the hydrogen index versus the oxygen index for our kerogen maturity, we also kind of like put side by side our results, which we have here, and that of the Engelmann and Sigler in 2015. We can see that our source rock kind of like have could be given a type 2 to type 3 kerogen signatures, and type 2 dominant from our study, but definitely type 3, which indicates that hydrocarbon has already been generated. So we can see our sediments here kind of like fall within the type 3, but Sigler and Engelmann kind of like had years between the type 2 signatures. Taking a look at the plot of production versus maturity of the source bed, also fixing our plots, our samples in our studies with that of Engelmann and Sigler in 2015, we were able to discover the Birdbear source bed are thermally matured. We can see they are also thermally matured and are within the oil generating window. And we can see that or the decrease in hydrogen index, which also gives us increase in Tmax values. And with the Tmax values, definitely we are able to see about 450 degrees Celsius of the Tmax, which indicates that oil has been generated within the sediments of the Birdbear formation. So higher Tmax values indicate higher hydrocarbon generation within the sediments that we looked at. On our discussions, we'll see that sediments in the Birdbear did undergo high significant diagenesis. Various phreatic sedimentation diagenesis were undergone by these sediments. We also saw VOGI, solution-enhanced intracrystalline and intercrystalline porosities that were bound within the sediment. The source bed here, as you can see, were thermally matured with the oil and are within the oil-generated windows. We also saw type 2 to type 3 corrosion signatures, which indicates matured oil-generating samples. And the production in our samples shows that they are localized within stratigraphic traps in some areas. But there are potentials from a well 12962, which has a potential for high hydrocarbon production. And we can see that production depths are within or approximately 10,800 feet. So in conclusion, we're able to see that the Birdbear formations has distinct anhydrite, dolomite, and limestone lithology that are easily identifiable and traceable across the Williston Basin. Significant diagenetic alterations in the Birdbear produce excellent reservoir and increase effective porosity and permeability within the mapped area. And production is present in the Birdbear as kind of like debunking other theories that is not not visible, but production is localized within stratigraphic traps at some depths, approximately 10,800 feet. Source rock present in the Birdbear is self-sourced from two important porous zones, the A and the B, but most importantly from the B unit. And we also see that the Birdbear appears to be at least partly self-sourced hydrocarbon formation and contains distinct beds that are organic rich. We can see from other studies between 1 to 11% and are oil prone, and these sediments are thermally matured. My acknowledgement, my references, and thank you.
So, questions for Francis? I was going to say, I knew Jeff Bader would have one.
Hey, can you go back to that map where you showed the porosity across the basin there real quick? I have a question on that one. There's a very linear, that one there. So there's a very linear trend there kind of in the middle of your square, you see, where it says low, and then it goes down to the south of higher porosity. Do you have any idea what's going on there?
This area you're talking about?
Yeah, and then from down where it says low, you see the green?
Here. Definitely some bullseye porosity.
The north-south trend. See the north-south trend from low all the way down going directly south? You see that green trend?
This way?
Very linear.
This
Yeah.
way?
Is there like a fault there? You think?
Probably there could be a fault there. It's possible there could be a fault. That could have enhanced the
So
porosity
there
in
is,
that area.
you're looking at also, you said stratigraphic, probably some structural
Yes, structural, yes.
influence
Yes.
too? Yeah, I would agree.
Yeah,
Okay, good talk. Thank you.
thank you, sir.
I was going to ask, so you had God Almighty above me? Is that the pecking order?
He made us all,
Acknowledgements?
so.
Okay. I think Steve's probably got a question.
So what type of corrosion do we have with this Birdbear?
Type of corrosion?
Yeah.
It could be 2, it could be 3. My samples were 3 because I believe they have generated while we were running the samples. But you can see Ziegler and Eagleman, theirs were type 2. So, but
Okay.
it could depend on where you are in the basin.
Now, most of the production of the Birdbear is oil?
Sorry?
Most of the production is oil?
No. It could be gas, it could be
Okay.
tar, it could be something else.
So
But
2-3 could
definitely
check.
not all oil, no.
Okay, so 3 could be a source rock.
Yeah, okay, yeah.
Francis, that was excellent.
Thank you, ma'am.
I see you have McKenzie County.
Yes, ma'am.
Okay, we did a lot of drilling down Golden Valley County, Billings County. Have you looked at any of those areas? You know, we targeted the A zone horizontally for, you know, for quite some time. Drilled vertically, you know, in the B zone. So have you looked into that area? And I'm kind of curious, this is all self-sourced?
I've not kind of like looked into other areas though, but to my understanding, I believe it could be self-sourced or, yeah.
Okay,
Yeah.
thank you.
Any more questions? If not, thanks again, Francis.
Thank you, sir.
Thanks, Francis. Our next presenter is Steve Nordeng. Steve is the Harold Hamm Professor of Geology at the University of North Dakota. Today, Steve is presenting using core scan technology to evaluate Williston Basin hydrocarbon plays and reservoirs.
Well, I'm sure nobody's probably surprised by the fact that in the last few months we've been undergoing quite a number of bait and switches on sort of the global scale. You're getting the same thing kind of here. I will be talking about core scan technology. I will be talking about something in the Williston Basin. As far as making it relevant to a hydrocarbon play or reservoir, might be a stretch. It's associated with a formation that does produce oil, okay. The reason for that, of course, is as you're going along putting together a slideshow or a presentation like this, you sometimes let lesser angels take over in the midst of things and you do something easy. And so that's what the point of this is to try to make use of this hyperspectral scanning technology that we had at UND a couple of years ago. And a couple of results that came out of this that ended up with some very interesting geology that apparently gave us a conclusion very quickly and very simply and doesn't require a lot of explaining, or at least that's what I thought. We'll see. Now what we did, and this is, I think we finished this in December 2018. We began this program probably in about 2016 and putting everything together. And what we wanted to do was to bring in a hyperspectral scanning unit, which we have right here. And we hired Core Scan Limited out of Australia, and they have a number of these units that are inside shipping containers that they ship around the various mining sites around the world. And we managed to bring them up here in November, or actually December, to Grand Forks. And you'll be gratified to know that the fellow right there is from Australia. This guy flew in from Indonesia, both of whom coming out of somewhat, I guess, warm conditions, and we were 10 below zero at the time. And they were having a hard time adjusting that. For what it's worth, this unit was inside the core library, so they were very grateful for that component. But what we did is that we basically photographed core. We did red, green, blue images, high resolution, and at the same time, basically mapped out and also imaged these cores from basically 450 nanometers up to 2500 nanometers. In other words, throughout the visible spectrum into the near infrared in the region of light we can't see, of course, and then subdivided this spectrum into 4 nanometer wide bands. So we essentially are looking at core using 412 or so colors. And these colors are imaged on a 50 micron basis, and then from those various reflectances and adsorptions within this spectrum, we can identify a variety of different minerals that might be relevant to oil and gas. Minerals in particular that contain crystalline water, or hydroxide groups, OH groups, carbonate, iron, amongst other things. So we can identify a variety of minerals such as, I guess, things like, well, smectite, illite, chlorite, kaolinite. Those would be some clays. We could identify, differentiate between calcite and dolomite. So that means you don't have to put drops of acid on your pictures on the screen anymore, see which one fizzes. Right? And so, and then see a few others, say gypsum, for example, has a crystalline water. So there's a variety of different minerals that we can identify using this particular technology, using photography. Now, like I said, we have a variety of different things that these people provided for us, one of which was a classified mineral assemblage that we were mapping out on a 50 micron scale. And we imaged these things continuously through the core. And the red, green, blue was at 5 micron scale. So we were generating enormous amounts of data. I think we were generating something on the order of 4 terabytes of data per week. We could not transmit the images to Perth to be analyzed through the internet. We had to physically send the hard drives. And they maintain these data now for us and have it online. What they did was they were able to put together various maps showing things such as crystallinity. In some cases, you can get grain size out of this, but more importantly, we could get spectral parameters that were related to specific mineral compositions, and they could map out these minerals that that the wavelengths are sensitive to on these about 0.1 meter scale. And then we generated logs from this, so we can then take the logs of the mineralogy derived from the hyperspectral scanning, lay them down next to our electric logs and see how they match up. I'm not going to cover any of that in this particular talk, but I did walk over this with the Red River Core workshop that we have online as well. I did a little bit of that. Down here, the numerical logs, and then all of this is accessible currently for free through CoreShed's server system. It's online, so it's accessible to everybody through UND. Here's a picture of what a core would look like. It's laid out side by side. These are what's referred to as a tray view, where the cores, these are 3 foot long, stacked up from the top to bottom. I believe it's top here, bottom. I think it's American layout as far as the cores are concerned. And what we're looking at here is the state, I think the state, Nelson State well. This is the Lodgepole, Upper Bakken, Middle Bakken, Lower Bakken, 3 forks, complete core, which we can view this way, or if we wanted to, we can switch the way it's presented into a standard vertical downhole view. There's a variety of different views we can also do. For example, this is a simple red, green, blue picture. We could then look at things such as the global spectral parameters, which the people that analyze these types of imagery use frequently. I have no clue. Okay, I look at them and they look like pretty pictures that are all grayscale. And they can tell things from these, I can't. What I rely on are their analysis of these grayscales, which we've broken down into basically 21 mineral compositions that we then lump together into 34 separate mineralogies, and then map the cores at a 50 micron scale for imaging purposes. And then the 50 micron scale is then averaged across each core to come up with the numerical logs that we can then compare to, say, other logs such as wireline. Okay, just to give you an idea of what the resolution is on this, we'll start to zoom in a little bit. Here we have the contact between the upper 3 forks and the lower Bakken, and zoom in a little bit and a little bit more. And you can see that this red, green, blue imagery is really quite high quality. We can pick out the laminations within the upper Red River quite nice. I can zoom in a little bit more. We can pick out very fine details. This is about the point of enlargement where it starts getting a bit fuzzy, okay? And my guess is you're probably looking at an illustration or something maybe just shy of a 10 power magnification, in other words, what you could do with a hand lens. So the point is these images are probably about as good a representation of what you can see in the core as if you were to actually pick it up in the core library and look at it. Of course, the downside is that you can't take this core and pick it up, turn it around, look on the end, and do all these things that geologists like to do, taste them, these things. We still have to come to the core library to do that. But what we can also do with this is that we can then take our red, green, blue image. Here's a mineral class map, and I probably should have a little key over here, but each of these different colors corresponds to a different mineral, a different lithology that was broken out to represent this rock. If I remember right, the yellow represents dolomite with ferrin dolomite. The sort of aqua blue there, that's dolomite. The blue here, I believe, if I remember correctly, is illite. And here we have the class map. Or we can separate out this core and also just put down the individual mineral components of interest. For example, this is the distribution of calcite within this core, distribution of dolomite, illite, chlorite. And this is in the Red River. And what you can see, of course, is it's mostly dolomite, illite, with the layers over here, these little laminations in here being consisting primarily of illite. The more massive material here is dolomite. And what's interesting, and I don't have any more illustrations of this, but someday, if somebody's interested, the upper portion of the Three Forks has a lot of illite. You get into the lower portions of the Three Forks below, let's say the lower portion of Three Forks, the clays become dominated by chlorite, which is starting to say things about provenance and changes in sediment supplies through the Three Forks time. But that's too hard, so I'm not going to talk about that anymore. But where we have this site, I'm going to sell the site. We have it currently up and running. If you go to the Geology and Geological Engineering page at UND's site and look over here, you'll notice we have a variety of things. My name is listed under faculty someplace, but down here you'll see this virtual core library that we've established. Click on that, and it takes you to another page. Okay, now this is a university. We do things the hard way. We don't log into the virtual core library right on the front page where it's easy to get to. No, we have to hide it. So we hide it underneath this label called Core Scan, and we label it under log into or create a new account with Core Scan, at which point we click on this and we leave UND and head off to Perth, Australia, where the server is kept. Core Scan maintains this core shed facility. All you have to do is input your first name, last name, an email address, a password, duplicate the password, send it off. They send you back an activation code. You enter that in, and then you are signed in. Okay, at that point, you can go to the front page of what's called a dashboard. You're confronted immediately with a Google Earth view of the world, showing the location of all the wells we have in this data set, right there in North Dakota. You can scroll in to zoom in on all these things, and we'll see how that in just a moment. But we have basically 5 categories of wells that have been drilled. Bakken, Three Forks, I can't read it. See, I'll have to go from memory now. See Bakken, Birdbear, Red River, Tyler Formation, and 1 Madison. Or total of 77 cores. We have 9,800 feet of core imaged currently, consisting of 38 of the cores being Bakken Three Forks, 6 cores that I'm going to give to Francis to play with from the Birdbear. We have 1 Madison well, 12 Red River, 18 Tyler cores imaged. Okay. Now, one of the things that happened very early on, this is the subject of this talk actually, is that I get this phone call, and one of the fellow that does most of the work for Core Scan, that does the, I guess, spectral mineralogy, a fellow named Lionel Fontenot, gave me a call from Perth. I'm very excited. And ultimately, I got through because, okay, he's French, he speaks Australian, and I grew up in the northern tier of the U.S. So and there was no subtitles. So we're trying to understand what he's saying. He says, there's allanite. Okay, finally figured out allanite, great. And he told me the chemical formula, KLSO4OH6, and I'm going, great. I have no clue what allanite is. He was excited because allanite is associated, and most of their business is with mining companies. This is frequently associated with hydrothermal gold deposits. And so he was excited that we were looking at, in the Tyler, hydrothermal gold. Okay, now I was thinking about maybe I'll run off, talk to Ed, start looking for hydrothermal gold in the Tyler. I thought maybe I better not do that. Maybe I ought to take a look at allanite again and see what else it could be doing. Turns out, and it's very interesting actually, we have these little pebbles here of allanite. First off, I was sitting there asking myself, okay, does this guy know what he's talking about? It's the first time I'm dealing with these folks, right? Allanite, gold, Tyler Formation. What did I just bought got this Studebaker I just bought secondhand, right? So I was going to check this out. So we got these little fragments in here. Turns out these are about the only 4 little fragments that you can see visually in the entire core. So we pull these things out. Okay, we'll test this. We'll pull the core, grab the drill bit, drill that out, and X-ray it. Right there. Turns out, we have allanite 12%. Woodhousite, well, okay, allanite is actually a mineral group name. These are specific types of allanite. Woodhousite, whitmorite, natural allanite, a couple of zeolites in there, and quartz. So yeah, you can't argue, I usually don't argue with XRD. So yeah, it does appear that that was in fact what they spotted in there. And the other thing is, allanite actually has a very unique set of spectral characteristics that these folks who deal with spectral analysis of mineralogy are very comfortable with. And for what it's also worth, this particular spectral analysis was used to confirm the presence of allanite on Mars, which is then used to argue that Mars at one time was wet. As we'll find out in a moment, allanite does precipitate from water. It's a very specific type of water, as it turns out. Okay, we have one modern analog that we can point to that is currently crystallizing allanite in a near surface sedimentary environment. And that's down in the Eucla Basin of Australia, radiating through here. Here's the Pacific or whatever, right there, landward here. And with the system, to just boil it down very simply, what is happening is we have Cenozoic sediments, sands, lignite, pyritic lignite, and shales. Overlying that, we have various other sediments and sediments containing a combination of things such as halloysite, allanite, and kaolinite. And the picture that the folks that have been studying this area in Australia have come up with is that you have groundwater circulating from inland towards playa lakes that are deposited behind a barrier set of hills right in through here, and you end up with high rates of evaporation. So groundwater is flowing through, evaporating, concentrating, and as a result, crystallizing allanite in here. Down here, we have a reaction between oxygen and pyrite forming H2S, then reacts with water to form hydrogen or sulfuric acid. Sulfuric acid migrating up, reacting within in their picture kaolinite, or not kaolinite, potassium feldspar. That reacts and then subsequently forms kaolinite, allanite, and halloysite. Okay, and this is the only place we have a modern analog for this particular system. This makes it simple, right? Okay, where are we finding allanite in the Williston Basin? Well, I would just mention that, well, the core we just had is Pennsylvanian. The Tyler Formation is right here. Basin of Melaleuca, right underneath the Alaska Bench, up here in, I think it's Devonian Stage, Pennsylvanian. Geographically, the core we're looking at here, the Morrison 1-14H, drilled by Continental, located up here in the middle of McKenzie County. We're looking at, this is a very good core, by the way. This is the only core of the Tyler that's complete, top to bottom. Okay, so we're starting up here, someplace apparently in the Amstead, down here into the big snowy beneath it, full section. I think we had this core out a couple of years ago for a core workshop, and it'll probably be out again. But what we're looking at here, of course, is gamma ray, density neutron, PE curves, resistivity curves, And over here on the right-hand side is where we've taken these hyperspectral scanned mineralogies and plotted those up. And the one of interest is right there. That's where the allanite in that particular sample that we were looking at is. It turns out that it wasn't just that one pebble that's allanite. We also drilled out some of the matrix material, the clay material, ran that through, that contained allanite as well. So it wasn't just the one particle. Okay, so we have that. Again, back to this picture. This is zooming in on that one poor little particle that set this whole thing off. Right there, that was diagnosed to be alunite. Right next to it, keelanite halloysite. Up here, hematite. Turns out the hematite, as a percentage of the entire rock, is quite small. It's mostly surface coatings on grains. But we have this keelanite halloysite allanite association, which, if you play around with some chemistry and put it into a phase diagram, which you find out something very interesting. Keelanite and allanite are stable along that line right there, which, if you plot this against log activity, sulfate ion and pH, you have a very narrow range of high sulfate concentration and very low pH. So what we're looking at is, well, essentially a groundwater acid solution, essentially dilute sulfuric acid. And as it also turns out, and is because it turns out this is also quite rare. Like I said, there's about one known place in the modern environments that have this this particular type of chemistry, and that's this place in southern Australia. So what we're proposing then for this upper portion of the Tyler Formation is similar to the model that they developed for the Australia, where we have groundwater circulating through the upper portion of the Tyler, reacting with coals and organic-rich sediments, where we have the pyrite reacting with water to form hematite, which we see in our core, plus the hydrogen ion, and H2S. H2S reacts with oxygen, forming sulfuric acid. That disassociates to form, well, hydronium ions and sulfate anions. Up here, we have dissolution of illite. This supplies the potassium and aluminum. That puts that in the solution. We have silicic acid forming as well, which if we lose a couple of water molecules, we form quartz. And then this, under intense evaporation, is sufficiently high concentration of the sulfate ions and the potassium and aluminum ions, produces allanite. So it's a very simple picture, apparently, and we can maybe argue that the upper portion of the Tyler Formation had this particular type of environment with this groundwater activity that produced allanite within this sediment. Now, turns out this isn't new. This study was done back in 1998 by Benison and a group of other folks. They looked at 3 wells that were up in the Opeechee equivalent or Permian red beds, and they found the allanite in there, one of which is up here in western North Dakota, the Gulf Romanisian 2-33-4B, and they sampled the Opeechee between 7344 and 7689 feet depth. They found allanite in there, and that's where they came up with this model that maybe during the Permian, within the central portion of the U.S., we had these acid groundwater systems developed as well. What's interesting, however, is that the Tyler is at 83-82 in this well. I have not looked at this well to see if there's allanite that deep, but the fact is that in the Morrison well, if we have allanite in the top of the Tyler, that puts it not in the Permian, puts it in Pennsylvania, and that we have the same type of system developed. So it's not unique to the Permian. It may also be present in the upper portion of the Pennsylvania. So we may have some very complicated types of early diagenesis occurring in these rocks. So the conclusions are basically we can identify keelanite, halloysite, and alunite using hyperspectral scanning. And with a little extra work, we can come up with a bunch of other minerals. Now, the minerals that we found in that Morrison core are similar to the ones that Benison found. And we can, based on some basic chemistry, argue that the mineralogy in the upper portion of the Tyler was generated by acidic groundwaters modifying these sediments, and that we have this occurring during the Pennsylvanian. So I'd like to acknowledge the funding for this came primarily from Harold Hamm, Continental Resources, and the Petroleum Research Fund. We had a public-private partnership with UND that supplied the money for the scanning. North Dakota Geological Survey, including Jeff, Tim, and Kent Holland. You might expect that 9,800 feet of core involves moving several tons of rock off the shelves into the little trailer, back onto the shelves. We did this in 30 days because the state of North Dakota required us to get that trailer in and out because we didn't have a license to work in North Dakota. They gave us a 30-day window, so we got it in and out. Core Scan Limited, Brigitte Martini worked with us very early. She's no longer with them, but Lionel Fontenot was of great assistance in helping us work through the mineralogies, and he's still working on these projects. A lot of this stuff is still a work in progress. Many of these spectral signatures that we have, we don't have completely identified yet, and with time and some extra work, we may be able to tease out some more information from these. And then Nesheim Mahmoud in particular did quite a bit of the actual X-ray work with regard to the core, and Burke Brunson. These are both PhD candidates at UNT. Oh, that's if I ran out of time. Okay, any questions?
Questions for Steve? I'll start just real quick. Petroscan versus core scan, the value in those two.
Well, Petroscan is the company, and Core Scan is what we somehow got into the title of the talk.
As far as the, and when you look at like Tyler and you're able to look at the clay mineralogy as far as looking at doing acid jobs and using water, and you're looking at swelling clays and all these, so you see some real value in what they've been able to point out.
Yeah, well, like I said, the thing that the hyperspectral scanning is really good at doing is picking out minerals that have crystalline water, okay, which means smectites, illite, well, not so much illite, but smectites, OH groups that are associated with clay minerals, and the iron content give these things all specific spectral signatures they can pick out. And the idea being that you can look at these analyses or these hyperspectral scanning, pick out smectites, which might be sensitive to how you treat it with frac water, things like that. Also chlorites, it seems to be another big one. And let's see what else. And carbonates, that's the other one that's really quite good at, is differentiating between.
Where did your core scans take place? Did they
In the core library.
in the core library?
Yeah, what they did, they have this shipping container, standard shipping container about the size of this stage, and they basically put that on the back of a truck, shipped it up here. We got a front end load, a couple of them front on, dropped them off, put them on wheels, rolled it into the core library, plugged it into the outlet, and set up shop. And then they ran, we got students to run core through it. And,
Is that in Grand Forks or where?
yeah, in Grand Forks.
Oh, okay. Is it possible to do this while you're boring?
Well, you're what?
Is it possible to take these scans while you're boring?
No, this has to be on core. And the core we were using has been cut. Now, I think in the mining industry, they actually prefer to do it on core. They split with a vise. Rather than cut it, they just put it in a vise and split it so it's got a rough cut. And they do that because the way it breaks tells them a good bit about the rock properties that you can't see from a cut surface.
Any other questions?
Are you able to scan cuttings?
Yes. Well, I don't scan them. I haven't scanned them. What I was told was they can. But basically, the technology is very simple. I mean, they have a light, a broad white light. They calibrate this versus several standards they use. Then they have this essentially $1 million camera that then scans the imagery across this, was it 400 to 2,500 nanometer range at 4 nanometers apiece. So you're getting a picture of about 512 colors at 50 micron scale. And then from that is what you then work out what the mineralogy is. And yeah, it'll work on cuttings. And I think there's probably a couple of outfits out there, core scan themselves in Australia, might do it. There's other companies around that I'm not overly familiar with, but I know there's one in Madison that has a similar instrument that I've worked a little bit with scanning pieces of core, and they've expressed some interest in maybe doing some work with cuttings as well. This is the technology I don't think a lot of people have used much. And we'll someday find out if it has any real value.
Steve, did you mention costs?
Okay, what we did the cost on this was $15 a foot is what we budgeted. I think the total project, I think we spent $115,000 is the total project cost. That was set up, shut down, students, everything. I think we got a heck of a deal, actually. I think you're feeling sorry for us.
Anything else? Seeing none? Oh, one more.
So, not to leave the geology side out of it, you talked about the Tyler and the fact that you're looking at kind of a shallow environment. Does that unequivocally say that the Tyler is more of a marginal marine nearshore versus a more offshore?
Well, that's the part we didn't get into. If you get down into the section in the Tyler, you're looking at what marginal marine deltaic, I think, is some ideas, and where those organic facies come in that are real high in TOCs if they're deep water, or maybe something more lacustrine. This is telling you that at the top of the Tyler, if we got the top pick correctly, we're looking at a transition from marine to non-marine environments. And this is one of the things that actually kind of intrigued me with this idea that sometimes not with hyperspectral, but just this groundwater problem we have with Tyler, because our portion of the Tyler, if you look at the core, you can see individual stratifications within it, and some of them are very organic rich, and you'll notice that in some places you'll see what looks to be a front, a reddish, the oxidized iron red cross-cutting the laminae that contain black organic material, with the black organic material being bleached out on one side, and on the other side it's still there. So it looks like you have some sort of reaction front, some sort of fluid front that reduced on one side, oxidized on the other. And this, of course, pops in there, and I go, well, that makes sense now.
Sure. Yeah, it's interesting stuff. You can see things like that will give you a better idea for its depositional setting.
Well, I did it because it was easy. I mean, the allanite, if the allanite wasn't in there, I'd have to come up with a different story. This way I can borrow somebody else's story and plop it in here.
Well, it adds, you got the coal in there too. It probably represents inland maximum flooding when the water level is very high, and you got the percolation of that water and groundwater through there. So it makes sense.
So those of you who weren't here for the first part of the session, we needed to move some things around. So our final speaker is Alec Pollard. He's a geologist with Hybo Resources. Alec agreed to speak here several months ago when we were hoping that the border with Canada would be open. We're close, it's supposed to open next Friday, the 21st. So we appreciate, though, Alec got his presentation on on video, and so we're going to be showing that now. And Tim Nesheim, I think, Tim, if you would please come up when we're done showing it. Tim's worked on these same rocks on the North Dakota side, and just have a couple comments on Alex's presentation, and then maybe you'll be able to answer a few questions that come up. So the title of Alex's presentation's Widespread Petagenesis of Early Mississippian Carbonate Sand Bodies, Williston Basin, Saskatchewan, Canada.
Hello, I'm Alec Pollard. I'm a carbonate sedimentologist working in the Canadian section of the Williston Basin. And I'm going to present to you the widespread petagenesis of early Mississippian sand bodies. And I do enjoy this little background screen because it shows the complexities. So essentially, it's a core study of the Frobisher member in the Mission Canyon Formation. These Frobisher beds are commonly interpreted as ooage shoals. The fabric within the shoals are the product of petagenesis. And if we can, just a quick little preamble on why they're interpreted as ooage shoals. This is a legacy interpretation done by excellent work by Tuzesi in the early 60s. And he had very little well control, and pedogenic fabrics were not really understood at this time. And that interpretation, as good as it was, has been just utilized and reformatted and tried to, basically people are using his observations and interpretations and trying to put their observations into his model. Also, people have used a lot of textbook analogs to try to understand these rocks, and textbooks, as I've kind of pointed out in my core conference submission, these models are idealistic at best. They're not accurate for interpreting the basin. You need to really look at your observations and lean heavily into sedimentological principles, and you can easily modify this old model, and it simply just doesn't work. And they're all kind of creative ideas out there, but none of them are really based in sedimentology. So location and stratigraphy. We're in the Williston Basin, and that red box, I'm just going to turn my pointer on. The red box here is my study area. There's a swift current platform, and you can see that my study is essentially in southeastern Saskatchewan. So paleogeographic, this map right here is an idealized section done from a lot of work by Bill Gatenby, and so a lot of thanks to him. He's a fantastic geologist, and I think he's kind of he's in retirement, but he's interested in doing outreach with students. And so essentially what Bill's map is really showing is that these shoals are perpendicular to a paleo shoreline, and he's identified the shoreline as Coteau, Bluel, and Sherwood. And essentially the best part about this map, and I think he's basically spent years kind of putting it together, is that it just shows the orientation of these shoals along paleo shoreline. So it's not exactly perpendicular, but it's basically at an angle to the paleo shoreline, which is something that can be observed in modern sand bodies. So isopac map of my study area. These stars are the cores that I will be presenting today. And again, just kind of look at the orientation. There's the channels, there's your shoals. And then on the shoals, like basically the top is, these are, the tops are thins and it kind of thickens out. So basically you can see like there's an elevation decreasing as you go. Well, yeah, so essentially it gets deeper as you get off the shoals. So these will be your topographic highs, and then these channels will be your lows. And the little black dots are just oil production. This map is not updated, so there will be should be more wells in this area, plus horizontal wells. So I have identified 6 facies through my core and thin section analysis, and the facies basically are highly repetitive. They stack up upon each other, and they show a shoaling upward trend, and the large scale trends can be correlated across multiple wells in the area. Facies 1, it's a fenestral peloid packstone, and so you can see the fenestral porosity all through here has been occluded by calcitic cements, but there are some open voids, And if you look at the sediment, it's mostly peloid. There's a little forearm floating around. So it's like muddy peritidal fabrics. There are some the non-skeletal components are widespread, whereas the skeletal components are pretty rare. They're just mostly like scattered throughout the muddy sediments. Next up, next is facies number 2, and this is a peloid coated greenstone. So there are some coated grains. Essentially, you can see that some of the nuclei of these coated grains are ooids, like there are some ooids scattered around here, but what I really want you to focus on is the generation of the cortices afterwards. So we can see some cracked grains, and we can see some re-healing of these grains, or we can just see strange facies 1 type nuclei with irregular radial and radial cortices. Then there's some irregular cortices above, lots of cracked grains. Non-skeletal components are really the dominant ones. Skeletal components, you do get some ostracods, bivalves, and gastropods, so not really a very open marine type faunal assemblage, that's for sure. And your porosity is essentially vuggy, moldic. You can get fenestral porosity, and you get occasional channel porosity. And if you can see, there is a little bit of interparticle porosity. Also notice the meniscus cements between grains. That's pretty important too. It tells you that there's a lot of diagenesis taking place in the meteoric or vadose zone. Facies number 3 is a coated grain greenstone rudstone. This is a brilliant little thin section shot here. You can see the scale 2 millimeters. I mean, when I look at this piezoid, it really tells you a very interesting story. So as grains are being generated or produced, they are then being altered significantly in the newer environment that they're resting in. So just to kind of explain what we're looking at, we can see irregular cortices, several generations of them. There's voids between each cortic lens. There's some porosity between these grains. There's lots of evidence of these generation of multiple zones. So if you want to start at the beginning, we have this piezoid that's been formed. Its nuclei is facies 1. It has some irregular cortices taking place. There's some grain cracks, and then it's been basically amalgamated with another coated grain, and it just gets larger and larger. And this only happens in a subaerial environment. Skeletal organisms, very rare. So again, it's restricted peritidal environments that are generating pedogenic structures. The key characteristics are these irregular cortices, TP structures, shrinkage cracks, and then inverse grading. What's really magnificent about this too is if you look at this grain over here, it's showing a different type of generation. It's not as large as this piezoid. Its nuclei, again, is facies 1. You have radial cortices and then irregular cortices. So it's just basically showing each ring is being generated in a specific environment. But then at the end of the day, they're all getting amalgamated and subaerially exposed, and then going through contemporaneous diagenesis, essentially. Facies number 4 is a multiple complex crust. I call these calcrete crusts. They can be known as calcrete laminae or laminated crusts. Essentially, these are all just formed by degassing. As moisture is evaporating into the atmosphere, it precipitates. There's a drop in the partial pressure of carbon dioxide, which decrease the acidity, allowing for the carbonate minerals to precipitate in these calcrete crusts. And these only happen in subaerial environments. So here we see multiple generations of these crusts. And this one as well, we see the same thing. What's really fascinating about facies number 4 is that it actually traps facies 3 and also facies 1. So you can see these multiple cycles being created, and then they're going through diagenesis, and these are all basically responding to climatic subaerial exposure in an arid setting. Key characteristics are alveolar structures. So what I'm saying by alveolar structures, basically rhizocretions or rootlets, and 6 centimeters of stack crust, and they have this kind of like cream to buff color. Facies number 5 is the argillaceous mudstone waxstone, rare peloids and coated compound grains. The components, there are rare peloids aren't skeletal. Anyway, so what I'm really trying to say is that there are some ostracods that are scattered throughout it. Those are the uniform assemblage. Again, super restricted, not a marine setting at all. And then just if you look at these silt-sized angular grain, shows that there is an aeolian input of siliciclastics. Then facies number 6 is completely different to the other facies, and it's pretty much more of a marine assemblage. And I call it a skeletal packstone, greenstone, rudstone. So here we have echinoderm stereums. We have the pelletozone assemblage really coming through. You see some crinoid stem here, broken bits of bryozoans. Here's a broken fenestral bryozoan, just the outline of a foraminifera. Lots of peloids, coated grains in here as well. Broken bits of bivalve fragments. So essentially, this is very similar to heterozoan assemblage. And you only ever see facies 6 within certain geographic areas. And I'll just, this is a short presentation. So these only occur within the channels. And you can tell that a lot of the grains are fragmented except for the echinoderms, the echinoderm stereum. So basically coelacanths. And they're typically grazers. We can prove that in the Miocene. So essentially, they feed off of algal deposits. So these are rather large. So I imagine that these guys are just kind of cruising around, eating whatever they can. They're not exactly, they're more cleaning your aquarium tank, I guess. Facies distribution, you can see this little cross section here of all the wells that I've looked at. And there's this kind of repetitive nature, and I basically picked it from the Frobisher evaporite. And you can these argillaceous sections, which are known as marker beds of people working within the basin. And I'm using the American terminology, but you can use the Canadian terminology, the Huntoon, Griffin, that whole section is essentially the same thing. Some beds are kind of lumped together, but the blue well essentially can be split into 2 units up here in Canada. And what I really want to show here is that we have these repetitive, we have a little bit of a marine signature at the bottom with some ooids, but then essentially you get into this pedogenic development with calcrete crusts and piezoids, marker bed, peloids, coated grains, larger piezoids, crusts, marker, and then this situation repeats some rootlets and stuff too. This is kind of widespread. The only difference is the off crest and the channel. In the off crest, we start to see cross bedding. I would say these are more ripple laminations. They're not really dune structures, but in the channels, you can see cross beds all the way through. The argillaceous markers are not present because they're basically, this is forming underwater, and the argillaceous markers are interpreted as the maximum regressive surface essentially. So these sediments have been exposed the most. And I can see in the channels that some lagoonal, very restricted type sedimentation. I would say lagoonal, I don't want to throw you off and think that there's a lagoon here, but essentially you start to get that restricted sedimentation that kind of align with the, on the shoals there, marker beds. If we kind of look at the pictures of the core as we move up through the section. This is from a crest core, kind of at the bottom, and I have facies 3. We can see these large piezoids, smaller coated grains, peloids, maybe some scattered ooids, large piezoids with irregular coatings like I talked about. So that's a classic pedogenic profile. Here's facies 1, that peloid fenestral mudstone, waxstone, with some coated grains in there, which grades into facies 2, which is the coated grain packstone, greenstone. So essentially, I really like this picture here because it captures 3 facies. This is the most pedogenic development on top. There's a bit of an erosional break, and then we have facies 1, facies 2. And this thin section came from facies 1, and here we have an Ortonella bush. You can see those kind of little rod-like features of this calcium microbe or calcareous algae. And it's surrounded by this soupy matrix and some compounded grains. So essentially facies 1, that's kind of just rounded off. And if we move up, crest core, facies number 3, a lovely rock shot here, and you can see beautiful piezoids with irregular cortices, grain cracks. You can clearly see that in the core with no magnification, surrounded by lots of piezoids and coated grains and peloids. This picture here, it was in the front of the presentation, and it's my favorite. I mean, essentially, you have facies 1 as your nuclei. You have the irregular cortices that display grain cracking, and then micrites or mud, facies 1 type sediments being entrained and then recoated. And then you can see this kind of erosional surface here, where the piezoids kind of been broken up but preserved at the top. I just find that fascinating. I guess one thing I should talk about is the generation of these cortices. So after you have your nuclei, there is a period of moisture. So we're in a semi-arid climate. There is some rain, sea spray, Inundation by tidal waters doesn't really matter as soon as these grains get wet, it creates a microbial gel, and the gel essentially dries under subaerial exposure. The partial pressure of carbon dioxide decreases, and then the carbonate minerals start to precipitate around these rings with the aid of microbes. So still within that line of my legendary mentor, Noel James, he always said that carbonate sediments were born while siliciclastic sediments were made. And that's essentially true here. What's great about this picture as well is we can see what people would call an ooid because of the size, less than 2 millimeters. But when I look at it, they have a cracked nuclei. We have radial cortices, irregular cortices. So it's actually just a bit of peloid mud, like carbonate mud, that's creating a nuclei, and then you have these generations. This could be happening. These first radial generation could happen, in supersaturated, magnesium-rich waters, and then the irregular cortices are really happening in a subaerial environment. So essentially, the grain generations, each cortice will tell you what environment it's been precipitated in, which is fascinating for me. If we go into the off-crest core at the base, I just wanted to show this kind of a little bit of microkarsting. Here we have facies 1, it's just like a mudstone. Actually, no, sorry, the green color, this is an argillaceous mudstone, and we can see some erosion, potentially bioturbation, but this really looks like microkarst erosion. So essentially after this argillaceous marker was semi-lithified, it's been eroded and incised, basically forming this little microkarst feature here with the newer sediment coming in on top and also infilling voids underneath. And this thin section is right from this area right up here, and you can see the outline of the argillaceous sediment, lots of eolite, it's peloid. It's basically like a carbonate mud with siliciclastic grains, angular, very fine, probably aeolian distribution. Then you have this kind of like the coated grains, piezoids, a little bit of skeletal degree, it's just echinoderm spicule in there, and a lot of aeolian dust as well. That's fine, angular silicides quartz. If we go further up the off crest, and this is the ripple lamination. So here we can clearly see these banded ripple laminations, and that's exactly what you'd expect to find on basically in the flank of a shoal. As the tidal currents are coming in and out, they're creating ripples along the edge, and that's really preserved here. That's exactly what I want to see in an off-crest core. When I look at the sediments in here, there are some ooids, there are broken corroded grains, there's facies 1 mud that's kind of, I wouldn't call it exactly like a rip-up class, but essentially it's just been, ripped up from carbonate mud and kind of preserved in this matrix here, and you can clearly see the banding. But also notice like this band here is a higher energy deposit, and I can see the pelletizone assemblage, as I like to call it, which is like crinoids, bryozoans, bivalves, and so on like that, just kind of put in. So it's a heterozoan, and the pelletizones are the crinoids. Core, very marine. All of these forams, these planktonic forams, some benthic forams, kind of scattered around, completely different faunal assemblage. This is, similar to an intertidal package. All of the grains are really packed into here in a nice greenstone, like I talked about. Right off the bat, you can just see a completely different faunal assemblage to what we saw before, just like rare gastropods and ostracods, very restricted kind of paratidal sediments. And then when I look at a thin section from this rock, what do I see? I see a coated grain, I see an echinoderm sterium, some spicules, lots of forams, broken bits of like bivalves. Everything is kind of abraded and amalgamated. So this shows a heavy transport regime, and that's why it's interpreted as a channel. So you can imagine tides fluctuating in and out, and these are concentrated in the lows, and that's why we don't get the marker beds and those argillaceous sediments, but I'll describe that model later on. But what's fascinating to me is at the top of the channel core, we start to see that pedogenic development. So when I look at the rock shot, it looks kind of dirty. There's some anhydrite crystals in here, calcite cements in the voids, but you can kind of see these kind of ghost fabrics, but these are coated grains. And when I look at a thin section, it is kind of dirty. There is that aeolian delivered silt kind of scattered throughout there, those angular quartz grains. And you can kind of see the outline of some compounded grains and some coated grains and piezoids. So it's fascinating that at the top of the channels, they're showing subaerial exposure. So my facies model, essentially, here's a cross section. We have a top of a shoal, a crest of a shoal, and our channel deposit. And essentially the channels concentrating that hydrodynamic flow, the tides coming in and out with the tidal channel dominant going inboard and then less dominant coming out. So I should actually have an arrow pointing the other way, but that's something I can fix. So here we have our faunal assemblage, kind of intertidal marine, the peltazone crinoids, corals, bryozoans, ooids are being formed, coated compounded grains are kind of amalgamating further inboard, and these particles are being transported into the off crest where they start to undergo pelagenesis when they're subarally exposed, as we can see right here. And then the final goal is extreme subaerial exposure, where you're getting that calcrete pedogenic development of the crusts and the irregular cortices around the grains that have been basically amalgamated. So you can have grains from the crest that roll down into the channel, absolutely. They just get reworked and removed around, and the energy is coming from the channels. So essentially, I've kind of been alluding to this, but it's a complex system of deposition and near contemporaneous alteration. And we'll look at basically how I'm kind of building this model. So the first depositional cycle, so let's say this is the Sherwood. We have some right across, here's our channel off crest or flank, and then our crest top at the right here. So in the beginning, we get a lot of ooze, a lot of marine deposits. In the channels, we start to see dune formations, as I point out here in this rock shot. Here's your centimeter scale, and you can start to see these, like, it's almost a dune formation. It's like, this is a dune. I would say this is a simple complex dune because there's a little bit of a trough being formed here, and then you have your angular cross beds. These ripples that form a nice dune coming up. And the faunal assemblage is high energy, lots of ooze, broken skeletal debris, and very classic of the channel. And then as you go through your first kind of exposure event, you're basically getting restricted peritidal cements that are being preserved in your muddy flats. In time 2, you're continuing with your erosion and deposition of these into intertidal faunal assemblage of the, bryozoans, crinoids, bivalves, ooids, coral fragments, essentially forams, and that's being continued to be reworked and distributed within the channels. But up on the flanks, your carbonate production is essentially through sea spray, wetting and drying through rains, and subaerial exposure. The vuggy porosity that we can see is essentially being enhanced by the tidal flux, which forces the air. So gas is running through these shoals as they can to kind of expand the vuggy porosity that's being formed, and you start to see some colonization of plants and gastropods, beloids. So essentially, your channels are showing basically funneling the energy, and that's why you're getting that kind of intertidal deposit that shows heavy reworking. And then your shoals are actually where you're getting your carbonate production through diagenesis, subaerial exposure, and remigrating of sediments from the channel are making their way onto the shoals, where they're undergoing pelagenesis. Time 3, so this essentially is the koto beds at the flanks, the ripple marks that I talked about, which is what I'd expect to see in a tidal system. And again, in the channels, it's the same story, focusing the hydrodynamic energy. Up on the crests, it's where your carbonate production is through deposition and diagenesis and colonization by plants. And so for the alteration phase, which I've alluded to previously, we can see as the sediments being deposited, they're starting to undergo pedogenic development. So you're getting these large coated clasts. I can't even call those like piezoids. It's so large. It's a piece of lithology that's been separated and recolonized and showing that kind of cortex development in a pedogenic setting. On the left-hand side, these are called comets. They're essentially groundwater calcretes, and that's a section in a paper that I've just written about this work that I've done here. Essentially, it's the capillary fringe. So as water, just at the contacted the groundwater table and open air, it's that capillary fringe. There's basically evaporation and transpiration. So has that kind of like comet with a tail always in the direction of up. So that's a groundwater calcrete. More alteration. So as your particles are being kind of like I was showing earlier, as they're being, that peritidal assemblage is just resting there. They're undergoing pedogenic and microbial enhancement. What I liked about this one at time 2 here in the channel, I can start to see pedogenic development. So that's showing that's an overall regressive system. You can see that, channel sediments, then a little bit of a transitional zone, and up on the channels, essentially like that's your maximum subaerial exposures occurring over here. And then time 3, before the evaporites kind of coat everything over and create a fantastic seal, we have the concentrating your pedogenic development. So this rock shot up here shows calcrete crusts with facies number 3, and it's kind of repeating itself. Here's a thin section kind of just showing the same thing. Here's a large piezoid. The nuclei is actually coated grains, and this one has been fractured and rehealed, which is that kind of like broken grain with recoats over it. That's a classic pedogenic development. This rock shot here shows the same thing, lots of piezoids, vuggy porosity, which, like I explained, was enhanced through tidal flux, which concentrates the gases in the shoal, so the air is pumping through it and enlarging these pores. And then E is a great picture because we do see some ooids knocking around in here, but it's a large piezoid kind of floating at the top. So this is kind of coming from that kind of flanking area where you're getting some of the channel sediments just forming, and then everything is then going under pedogenic development. So just to kind of drive home my model, as you're approaching a high stand, you have your dunes and your intertidal sediments being washed through the system. And as you sit in your high stand, you're starting to get some subaerial exposure. So your muddy peritidal sediments now undergo petrogenesis. That's where we form those crusts and coated grains and those different facies. So my little arrows here are showing tidal flux going in and out and constraining the erosion and reworking of intertidal sediments. And as we dip down into our low stand, we have a lot of exposure. Our argillaceous sediments are being developed. Our dunes and our channels have already been preserved. We're just stacking more of it. That's why it's so difficult to pick the channels, to see those marker beds, because the marker beds are not having the opportunity to be formed because they're being inundated and eroded by the channels. By the waters migrating through the channels, essentially coming in and out with the tides. And as you go back into your high stand, the whole process is repeated again. So for any of you doubting Thomases or doubting Susans, there's proof of this exact same fabric occurring at the exact same time all around the world. So let's take a look at some of these. So up here we have, this is from South Cumberland. These essentially are from pedogenic researchers across the world, focusing mostly on these sediments and how enigmatic they are. But essentially, this looks very much like my facies too. We see some piezoid. Sorry for the quality, but essentially these are black and white pictures that they published. So anyway, we have piezoids and we have that kind of muddy matrix. And if we go across here, this is from Scotland, and we see that, calcrete crusts, the same, that looks very similar to the Frobisher. We have coated grains, piezoids, ooids, all going under pedogenic development. So this could be the Frobisher, and this is all occurring at the same time. And then if we move across here, this is Wales, and we can see the laminar calcrete. So this is like the crust or laminar calcrete. It looks very similar to the Frobisher. And we go across here, and this is from Derbyshire. This is from a paper by Wright. We can see that this is that fenestral peloid. This is my facies 1, essentially. It looks exactly the same. Then we cruise down over here, and this is from Kentucky, United States. This is actually Pleistocene from Barbados. But on the top here, this is from Kentucky, a paper by, what's his name again? Richard Walls et al., 1976, I think. Essentially, it looks very much like the Frobisher. You can see your piezoids, your crusts, your clasts that are being recoated. So then we move on to this down here, and this is from Wales again. And this one, you can see rhizocretions and rootlets, which is very similar to what we see in the Frobisher rocks that I've studied. And then at sea, finally over here, this is from the Canadian Arctic, and it looks just like the Frobisher. So essentially what I want you to realize is that this isn't a special case. This same pedogenic development fabric is happening all over the world And what's controlling it is the climate, semi-arid climate, subaerial exposure, and it's not a coincidence that we're seeing it in the Frobisher, and it should be expected. So all around the world, it's happening at the same time. These are not OID shoals. You have to basically abandon the ramp textbook model and use your observations to kind of figure out what's happening. And there's great climate indicators. And this is essentially a world-class pedogenic deposit, the Frobisher member of the Mission Canyon. So my summary, the pedogenic alteration of grains and calcary development is observed within the crest and off crest and at the very top of the channel. The channels are showing more of that intertidal faunal assemblage, and when you look at the grains, and we've looked at them, we've looked at the sedimentology, and we can say, yes, this is a tidal deposit. Yes, the channels are focusing this tidal energy, and you're seeing the imprint of this tidal system on the off crest, where you expect to see it. And then just finally, the channel is a completely different faunal assemblage to the actual sand bodies or the shoals. Early diagenetic fabric is due to subaerial exposure and diagenesis. That is not even in debate. That is exactly what's happening, and it's happening all around the world at the same time. And you just need to only look at the observations, look at the deposition. The literature is out there. It doesn't take much to recognize what you're looking at if you understand the principles of sedimentology. Direct evidence showcase of tidal influence of sedimentation. I already discussed that. And finally, the same pedogenic fabric occurs in multiple geographic locations with the same climate at the same time. And in the background of this picture, that's actually from Bermuda. I did a field trip there with some people that I'm going to thank just now. And these are not the same because they're phosphate, because they were on a goat farm and the goat urine is basically converted from calcium carbonate to phosphate. And this looks just like facies number 3 from my Frobisher beds. And so it's happening at every occurrence throughout geologic time. And I guess I should thank a few people. I'd like to thank my friend and my mentor, Noel James. He's really guided me and taught me a lot, taught me how to write and understand and apply principles of sedimentology across multiple basins at multiple geologic times. I'd like to thank Bill Martindale for essentially teaching me how to log core, use the principles of sedimentology to build models from scratch, and to be not be afraid to disagree and agree with other people, and essentially use your observations to develop your models, not use somebody else's model and shoehorn your observations into it. And finally, I'd like to thank the folks at Vermilion Energy for all of their help in allowing me to present with you guys today. And last plug for the Ministry of Energy and Resources staff at the Subsurface Geological Lab, Richard Wood, Kelly Levardier, Paul Thompson, Dane, and Ryland. Thank you guys so much. I wouldn't be able to do the work that I do if it weren't for y'all. And I believe that you really, you guys have made most of my work possible. So thank you very much to all of those kind folk. Thank you very much for listening to my presentation, and do have a good day.